Okay, so now we'll turn to machine learning, and Harvey will continue.
Okay, well, since the introduction to high energy physics took a lot of the time, I thought I would jump to some areas which have great potential for machine learning and also where there are the first hints of concrete progress, and I'll try to include those. Okay, so there are a number of areas where we could improve things a lot over our traditional methods, potentially. First, you saw about triggering, how we do the real-time filtering of data to end up with tolerable amounts of computing and storage needed to extract the potential new signals. And also, the very operation of having many of these sites cooperate in terms of distributing the data, storing it at the right places or places which are favorable where many people can get at it more easily, and having both an efficient and predictable time to complete certain operations on that global ensemble of sites. That's also something where we could really benefit from new methods, both in terms of optimization and coming up with stable solutions. In terms of the physics itself, there are a number of areas we're starting to go after. One is new tracking algorithms for the charged particle trajectories that you saw, for identifying objects, for simulating things faster, and also in the end, well, low energy computation means a form of computation in exascale systems that we haven't emphasized so much so far. So this is just sort of to give you a sense of the problem, how we deal with tracking now. So you see a sort of generic inner detector with layers where charged particles going through provide you coordinates. In order to, from the mess of hits that you see in the upper left, how to extract the particle trajectories, remembering that you have not only the interaction of interest, but also many so-called pile-up interactions which are not basically of interest. How you go about from these many, many space points getting the trajectories going through space. So first, the general technique is you do what's called seeding. You try to find some track stubs. One advantage is the inner layers of the tracking detector tends to be a two-dimensional detector called a pixel detector, where you read out X and Y, and so you can make a stub in 3 space, and then you can go around to the next layers, which are basically give you a coordinate in 1 dimension, well, 1 dimension that's measured, and then there are different positions of these strips. To build a track, and we use a method which is most often used as a Kalman filter or variation of that. The combinatorics, as you'd expect, are enormous, and so the time invested is also very large. And as the complexity of the events goes up with the amount of pileup, it becomes more and more of a challenge, and eventually could be a dominating factor in our computational limits of our computational ability, and therefore to take best advantage of the data in the future. So this has been one focus. Another is we realize that we spend really billions of computing hours making simulations. So I described the process by which particles interact with the material in the detector, and through various processes, which thanks to the question I got, some of which I got to describe, you end up with electronic signals. So this shows a picture here of an electron coming into one of these crystals, and then the electron first radiates in the presence of the heavy material, of heavy atoms, and then the photons convert, and then the secondary electrons and positrons then again interact, and you get a whole cascade and a huge number of secondary electrons and photons which are tracked in these simulations. And eventually you get a measure of how much energy is collected in each crystal, and then the light is propagated to the photosensor, and this photosensor creates a signal, and there's a representation of digitization, and it takes a long time. So the question is, could we not somehow, instead of doing this ab initio simulation of all these details, somehow have a higher level representation, for example, through generative models, that would short circuit this enormous computational time. The next is calorimeter reconstruction. This shows some of the crystals which are in that layer. Light is produced, and then if you look at the time dependence, there's an electronic signal from the photodetector which is then amplified, and you get this shape, this particular signal. Now with pileup, you actually get the superposition of many of those, and we actually have an algorithm that untangles up to about 10 of those within that short time interval. And again, isn't there a better way to do your clustering from all these hits in the calorimeter, and then to extract the information you want in terms of pattern recognition, then identification, then regression to give you the measure of, for example, the energy of the particle that initiated all of this?
Is the untangling just based on clustering by proximity, or is there a characteristic shape that you look for?
There are characteristic shapes. As was mentioned, they're not all that well defined, so one would have to allow for a whole range of shapes. What you're seeing also is, so that would apply more to what happens on the right. In the middle you also see in time, so that's a simpler thing, and actually the first attempt to untangle up to 10 of those pulses has worked rather well because of exactly what you said. That's an electronic preamplifier readout. It has a very characteristic shape, and therefore the decomposition into multiple signals of a given shape, that was relatively straightforward. I have to say that even there, that until you were to revisit it to see if you can do better, we don't know. Another subtle statement I can make is looking at our ability to reconstruct photons. There may be a missing 1%. There may be a source of a 1% resolution that we don't quite understand. So you look at that as a problem or an opportunity. So we're hoping, and I'll refer to some recent work by Maria and Jean-Marc Vlimon, who works with her, and some of our students, on trying to take a lesson from scene labeling work. You know, how you have a complex scene, how you identify objects, and what you, but even more than that, identifying the objects turns out to be something that we are doing with our traditional methods, but how you compose the scene. You know, what is this event? That's where some recent progress has been made. Okay, so let me skip over the early things to the later things. So some of the things which have been done, there was a pilot program to try to do better, and now we're starting to do better in terms of multiple jets. So in an event, let's say I have a B quark which forms a jet of particles, because quarks don't appear in nature. Then if a W particle is produced, when it decays most of the time into two quarks, and that creates two jets. But if they're high energy particles, there's a boost, right? Remember relativistic boost, for those of you who remember any physics? So then things get folded together, and how do you untangle it? So gluons can be identified because they tend to be wider and have subjets which are different from the case of a quark. And so there's been some progress in identifying gluon jets from quark jets. There was some work done a couple of years ago. Neural network methods to discriminate events containing the top quark, but I'll show something along these lines which are better also in the trigger, which can be done very fast. And then also, this is really something which has actually had a physics outcome. So in a different class of experiments, where I have a very heavy detectors which detect neutrinos, so this is the NOVA experiment. What happens is neutrinos produced at Fermilab go 700 kilometers to a large detector in North Dakota. And from there, every once in a while, some neutrinos actually interact. And one of the important processes is ones in which an electron is produced. So you have neutrinos which are really, because of the way they're produced, of the muon type. And then when they travel, some of them change into a different type of neutrino, the electron type. And you see them if they interact and produce an electron. But those events are hard to pick out and very few. And a big struggle was made to identify the electron events. One of my former students, actually, Alex Himmel, was the one who came up with this technique of using essentially a convolutional neural network, but he calls it, for some reason, a convolutional visual network, because I guess the visual patterns are quite different between the signal events and the background events. And by applying this, he was able to get 40% better electron efficiency with the same background, and it's a faster method than what we had before. Before we'd have a library of showers of these interactions, maybe 30 million of them, and try to find the best pattern match. And that took a long time and also was limited in its efficiency. Okay, so here are some recent work. This is something you should follow up with Maria when she visits here, I think next month. So we've been looking at 3D imaging of LHC data, energy regression and particle identification. For example, we'll have a new forward calorimeter for the phase 2 at the LHC. Event classification using particle level information, I'll say more about that. Charge particle tracking acceleration. So we're starting to look at that. I would say we have a ways to go. And distributed learning, so learning how to parallelize some of these computational methods, and so a high degree of parallelism, for example, on jet identification has been done running on large facilities with many GPUs. And then also Maria and Jean-Marc, I won't see much more about it, have been looking at neuromorphic hardware for online data processing and event selection. Okay, so this is highlighting some of the data science at Hydrogen Physics workshops that she has been running since 2015. 2016 was at the Simons Foundation in New York, and there's some references to some results shown there. And the latest one was at Fermilab. So the focus is on new ideas and solutions in tracking, as I said, calorimetry, detecting anomalies. That can mean finding rare events. It can also mean that you can apply it to online operations of the experiment, and instead of humans looking at all these distributions online and deciding if something is wrong, having that done automatically and much faster. So, I mean, the idea is not only to investigate these methods, but also to develop new paradigms, at least applications, and to collaborate in developing perhaps also some innovative approaches. Okay, so there are 3 papers at the last NIPS workshop, and I'll refer to a couple of them. So the first is this so-called deep topology classifiers. This involves, you'll see the various methods that were used. Then calorimetry, particle classification, regression, and simulation. And I won't say too much about the track reconstruction. It's more on the side of an initial investigation. All right, so this is from a student with some results which are fairly recent. So the idea started in the summer of 2016. There was a student from Berkeley, Danny Whitacombe, and continued with a focus on how to apply this in the CMS high-level trigger, the part which is done with normal processors, but one could also imagine also applying GPUs. And then finally we got to this abstract image classification, where different types of particles which come out of our first stage of the reconstruction are then represented as simple shapes, and how the pattern of shapes on a plane, which essentially is unrolling the two-dimensional angular range that's covered by the experiment, how that could be used to distinguish different types of events. So this is a poster that was shown there. I'll go through some of this. So the problem is that the trigger has a non-negligible false positive rate in trying to pick out For example, if I'm trying to pick out events which come from the production of a top quark and anti-top quark, this was the target of this study. You can have simple criteria like a single electron or muon comes out, but some rare events with nothing but jets contaminate this. And this means you have to take a lot of events and store them for further analysis. So you waste a lot of CPU time and a lot of storage. So the point is, can you filter away a lot of the false positives with these new methods? So this is a kind of representation about how it works. First, you generate the particles in the simulation as 4 vectors. And you have 3 subclasses produced according to the rate you know from the standard model. How often you produce a top quark and anti-top quark. Maybe I can use this. So there's a sample of such events. There's a sample of events with so-called QCD with jets, and a sample with a W boson together with jets, because the W can sometimes produce a lepton. And then you reconstruct it with this fast program called Delphis, and it gives out particles. You can also do a pre-selection, so it makes it a little bit harder actually to do the discrimination, which is good in this study. And you see that the problem is that if you want to pick these things out in the trigger, that almost all the events, according to the predictions, are going to be QCD events even after the selection, and W plus jets. And the little sliver here, which if you add up the percentages, is like 1 event in 200 is a top quark and a top quark event. So the student, Tong Nguyen, tried the various methods. One is a particle sequence classifier. I'll describe what that is. The sequence of particles is in a certain order is taken as input to a recurrent neural network. The abstract image classifier, which I'll describe in a little bit more detail, and a high-level feature classifier, just using some high-level features of the events and inputting it to a fully connected deep neural network. This one, the pictures didn't come out very well. I'll try to lead you through all the information from the cells. What you would tend to get, if I just sort of imaged what's happening in the calorimeters, I get various cells with different amounts of energy. But it's kind of scattered, and a convolutional neural network doesn't do well with this kind of sparse data where I have important pixels, but they're kind of disparate, you know. They're not contiguous regions. So the idea is, why not transform it through a kind of filter where instead of these pixels, you just, knowing what you think from our earlier stages of reconstruction of the particles, just put an image there. And so the different types of images, you can sort of see in black and white if you look carefully, you'll see squares and pentagons and circles. And so that's what makes it up. So first, I'll come back to that. First, a fully connected high-level feature deep neural network classifier. There are 14 high-level features. So if I take you through, there are various things like the total amount of energy that you see flowing transverse to the beamline, looking in a plane perpendicular to the beamline, where the missing energy is, how much of it there is, you know, telling you about neutrinos. For example, when a W decays, there are neutrinos, how many jets, how many B jets. If there are leptons, what is its momentum transverse to the beamline, the angles with respect to the beamline, how isolated it is, and so on. And so this is the network that was used with 3 hidden layers, as shown there, and then the outputs being a 3-way classifier, W plus jets, QCD, or TT bar. The next one, this particle sequence classifier. The particles are ordered according to increasing or decreasing distance from the isolated lepton. So you take the lepton as sort of the guiding thing that's telling you about the class of the event, and then try to look at all the other particles and try to help with the distinction, the topology of all the tracks relative to those leptons. And tried various things. Delta R is a kind of measure in two-dimensional space. There are two angles. There's an angle with respect to the beamline. We actually use a transformation of that because it's invariant to a boost along the beamline. But let's say it's a measure of two angles, and then there are the individual angles, the azimuthal direction and the polar direction. Should you consider the momentum transverse to that lepton of the other tracks? It turns out that this first, delta R, was the best, and that the best ordering feeding into there is decreasing distance from the lepton. And so it was fed in through this so-called, this network with so-called gated recurrent units, and then to do the classification. And there's some technical things at the bottom about how it was run on a single GPU. Okay, so here are the results. So the different techniques, the particle sequence classifier, the abstract image classifier with different types of polygons essentially representing different types of particles, and circles were used to represent the missing ET, missing energy, and the high-level feature classifier. And so you can see the results, the so-called rock curve, which is the signal efficiency on the vertical versus the background contamination probability on the horizontal axis. And you can see that relative to the red curve, which is our classic way of doing this, the red curve, there's tremendous improvement in terms of what you can achieve in terms of much lower background contamination for a given signal efficiency. So, for example, you can have an efficiency of 99% in the best case with very little background. In fact, you can reduce the background you have to store by an order of magnitude.
Excuse me.
Yeah.
This is to be run online after the triggers, but before you actually store anything?
Yeah, the idea is to eventually deploy this in the trigger.
Right. So how long do you have to reach your decision?
I mean, that's a good question. I mean, basically, it's going to be a sort of a fraction of a second, but remember, there's the training and the inference. So the inference can be fast. And if we do this in the trigger, I sort of skipped over it here. This is, I think, the kind of thing you should raise with Maria, who's more deeply involved in this. But one would imagine that for the inference, you'd look in the real-time system, perhaps, of complementing the classical processors with FPGAs or something, just to be able to do this at a high rate. Okay, so then there's this calorimetry with deep learning. And so just sort of showing the results. Again, so you're trying to identify particles. And there are two cases here. One is to distinguish a photon from a pi zero. The pi zero, a neutral pion, always decays into two photons. But if the pi zero is a high momentum, then the two photons are close together. So it's somewhat could be somewhat difficult in distinguishing it. And so here, to make it harder, they've actually picked out particles which are difficult. So for neutral pions, where the photons are really close together, within 1% of a radian separation. And in the case of charged pions, which are trying again to distinguish from photons, ones where in the detector very little energy escapes from the layer, which for us would be the crystals. This is, I think, in a more generic detector, but same idea. That you have pions which normally would put a lot of their energy in the Hadron calorimeter, but in these pre-selected cases they don't, and then to make it harder and to show what kind of discrimination could be achieved. So in the case of the photon versus pi zero, with respect to the boosted decision tree methods, which are the previous methods, there's an improvement where you gain 9% in signal efficiency, but more importantly, you can reduce the background by 40% at the usual working point. on this plot. And then for photon versus positive pion, it's even more dramatic. So you can get 99.4% efficiency, which is a 5% boost in efficiency, but the background is 150 times less. And so I tried to put dots. So this was before. You see the fact that this one is really up very high. So you can move this point back. You can move to the left and still get very high efficiency, but with very low background. And the numerical results are summarized in the table down here. The delta R background is the ratio of background for the new method versus the boosted decision tree. There's a reduction effect of 150. All right, so then there was the hope of generative models, of being able to make images and then classify things, including new patterns based upon what you observe. And so this was the work that was referred to earlier, done by Atlas about shower generation. So there are a couple of nice papers which came out this year. This is one of them, which talks about this so-called Calogan. It's generative adversarial networks for calorimeter shower production. And so this is the layout. This just shows you can find this talk online. But there are 3 layers with unequal resolution, and they share the energy longitudinally, and you get a profile, a characteristic shape in each of the 3 layers. You remember that in the other thing I talked about, neutrino experiment, they took, in their case, different case, huge library of showers, simulated showers, to try to match. I mean, this is a lot better than that. So what they're doing, well, so in Atlas, there are essentially 3 layers in their calorimeter. So you have the electromagnetic layer, which is rather fine-grained, and then the Hadron calorimeter layer and a sort of tail catcher at the end, and they have different granularities. So when you do the grounds-up simulation, like in this program, which happens to be called Xeon, Xeon 4 is like the 4th version, you get all these points. So all that ab initio simulation of interactions of the material, in the material of the primary and all those secondary particles happens. This is an electromagnetic shower, so you get a shower of electrons and positrons there. But what you really read out is shown on the right, where you can see that there are some channels, and the color represents how much energy was deposited in the cell. And you can see there are, relatively few cells in the 3 different layers. All right, so this is the generative adversarial network. Most people in the audience know more about this than I do, since I'm learning this rather recently. And this is some of the results. So you look at the different layers. In the first layer, you have a small sample just to illustrate of some patterns in the first layer, and then the best match, which comes out of the generative adversarial network. And then in the second layer, and then the best match. You see for the real case, you see 5 of them in the second layer, and then you can see the best match from the network, and then in the 3rd layer. If you look at the global features of what comes out, for example, the distribution in the energy in each of the 3 layers, you can see the distribution matches fairly well. But if you look at the CPU power, it's really a tremendous advance. So the Xeon 4 time to generate a shower is 1.8 seconds. And then using classical CPUs, from 1 to 1,000 of them, how many milliseconds it would take. But the GPU is actually tremendously well suited for this. And so, running these things in parallel, you can go from 1.8 seconds down to 12 microseconds. And this was demonstrated I ran a set of demonstrations at the supercomputing conference, and one of them that we hosted was a live demonstration of this technique where large numbers of showers were generated, and then the images were moved to University of Chicago and Michigan from the place to facilities. So facilities were run at Berkeley Lab, for example, and some other sites where they have lots of GPUs, and then moved for further analysis and storage at Chicago and Michigan. And then this shows the training going on, moving the shower images to disk in the middle, and the utilization of the GPU. Okay, and so in 2 days they produced 205 million showers. Now, the last thing I wanted to talk about is moving towards this tracking machine learning challenge. These slides actually come from David Rousseau, and so I show this one just to keep in mind that the following one also are from him, just to give an indication. So the idea is that we want to optimize the tracking. You remember the generic layering of a high-energy physics detector with a tracker, then calorimeters, then muon systems outside. And so this focus is on the tracker. And the reason is that it takes so much CPU time. So the tracking is what dominates the reconstruction CPU time. As the pileup continues to go up, it's becoming more and more of a problem. The growth, in spite of our code improvements, seems to be growing somewhere between quadratically and exponentially. And if you want to go up to 200, it's not even clear at the moment what the number is like there. And you can see also a picture in a kind of generic detector, a simulation of all the hits you get in the tracker, and then in some of the calorimeters outside. What a mess. Okay, so we expect the CPU power per dollar to increase, of course. I mean, but only about a factor of 10 in 10 years, taking the trends that we see now. I mean, this is before there are physics changes in, you know, we're not talking about post-silicon electronics or computers beyond what we do now in terms of silicon-based processors. So we only expect a factor of 10. The experiments, the data taking rate will also increase by a factor of 10, but the events are tremendously more complex because of pileup. And we'd like to have a reconstruction technique that allows us to look at events with 150 pileup, or maybe 200, and have a familiar reconstruction time like what we had at 20 pileup. So we need a very significant speed up factor, somewhere between 10 and 100. And so how are we going to do that? Well, like I have said, our field looks at itself as fairly mature in terms of having investigated how to do improved track reconstruction for a long time. But given the progress in other areas, it looks like possible, maybe even likely, that we can do better. And so the idea of this tracking challenge, which is in the process of being formulated and will soon be proposed, is to tackle this problem collaboratively between our community and machine learning community. This was an example. When I spoke here last time, I did remotely actually, I referred to this tracking technique. So there were, for example, in the 2014 NIPS conference, examples of tracking. You see on the left, for cyber-physical systems, you see various tracks for planes and then a clutter of birds. And then to understand, you know, how to have the various tracks not collide with each other or encounter the birds, or on a soccer field. But this is somewhat different, you know. It's, for us, we're worrying about the CPU time rather than, you know, whether there's an accident or something like that. There's also the experience of the Higgs Machine Learning Challenge, which ran in 2014. And this also helped set the direction for this challenge, how it will work in practice. There were 2,000 participants. You know, Kaggle runs these challenges. That was perhaps the biggest challenge they had in terms of participation. The best significance that was achieved was already 20% better than with the usual hydrogen physics tools called TMVA, which is a multivariate analysis tool set. The boosted decision tree algorithm of choice, the boosted decision tree was the best. Now I don't remember, yes, it was XGBoost, and I found this very interesting. I came across this myself recently, that when we say boosted decision tree, we don't mean that. But it's rather well known, it seems, in the computer science community that XGBoost, extreme gradient boosting, is the best type of boosted decision tree. And there were many ideas which are documented in this proceedings of a workshop at NIPS 2014. I wrote down the reference for you. And its function was to show that some people can do better who are not in our community, and also raised awareness about machine learning in hydrogen physics. So this is a table of results, and the top 3 winners, you know, get some money, and you see the score in the middle there. But the best physicist was only 8th. And it seems that he dropped from the previous year or something by 7 places. And the best person in terms of using the traditional tools, TMVA, was down here. He was number 782. So that's a lesson. And he had dropped 149 places. So the idea, again, this is David Rousseau's slide, is, okay, we have a problem. So over years, we develop solutions. And then the idea is that you present your problem in a simplified way so people can deal with it in a straightforward way to another community. They address the problem and they solve the problem, and maybe it's better, maybe. And then you re-import not the exact solution because you have a simplified problem, but the approach and the methodology, and you get some benefit. And another way this has been presented, oh, yeah. So there was sort of wondering about how much time it takes to do this. So this was a nice picture which was presented in 2014. So imagine that we're the traditional experts. And what you see on the x-axis is the value of our ideas. And so we get a certain value. You know, it's not low, somewhere in the middle, and it's rather well defined. And then maybe non-traditional people come along, and a lot of the ideas maybe don't do as well because we've been working on it for years, but there's some evidence that the upper tail of the non-traditional participants goes beyond what we do. That's the idea, not only in machine learning, but in general, how it works with innovation. It's a nice illustration. Now, remember, this is a CPU challenge. So, the next slide here is there have been CPU challenges. This is the Harvard Medical School contest for biology big data problem, a big data problem in genomics. And the focus was to get the results in terms of how you, to carry this out, in other words, to sequence, what is the best result in terms of correct sequencing, but also considering the time. So in this plot, the time is on a log scale. And the best in-house solutions are the yellow and the red. So on the vertical axis, the score in terms of correctness is pretty high, but it takes an enormous amount of time. Look at the x-axis. And then there's these other, the challenge submissions, the whole cluster over here. So they got the same, or in some cases better, score in terms of being nearer to perfect. But you can see that it was sort of 10 to 100 times faster. So it says you can annotate 10 million sequences in less than 3 minutes, or 250 million sequences in about an hour on a laptop. So that gives you motivation. So here's hydrogen physics tracking. Looks nice once you have the tracks. But before you have the tracks, it looks like that. And so the hope here is that this fascinates machine learning experts, right? We hope. And so we hope with this challenge to engage them. There are some early results done from within the community, but never mind. Okay. Now, the other thing, which gets back a bit to physics, there are a lot of parameters to the value of the result in this challenge. Many of the tracks in that mess of points are not of interest. So low momentum tracks are everywhere, and they're rarely associated with the event of interest. We care about high momentum tracks. We sometimes care about tracks which are in the middle, the high momentum, in the middle of very dense jets of particles. We care about tracks which come from displaced vertices. For example, if we produce a B quark, remember the most common decay of a Higgs boson is to a bottom quark and an anti-bottom quark. It forms a particle, a meson, and then when it decays, often the vertex is displaced. So it comes out of the primary vertex, you don't see it, you see a track, but then it decays later. So tracks from displaced vertices may be particularly important. Maybe electrons. I think the question mark is because of the showering of electrons, even in the tracker, maybe it's considered difficult. But very low momentum tracks have nearly zero weight. Okay? So the point, again, to say is that, let's see, another, is pattern recognition. So we know how to get, once we know the points on a track, we know how to get the track parameters. So we're not asking for improved measurement of the track parameters. The main part of this problem is the pattern recognition, identifying which points belong to the track. So that's a big challenge. And we'll be coming out. I mean, there are already hackathons and people are already starting to try, but it will be advertised and be a challenge in the next months. Now, one thing I just learned is a current example of deep learning for real physics examples, physics advancements. And so this has to do with picking out jets that come from bottom quarks and from charm quarks and how it's being applied. So the idea, for example, if I want to identify a top quark, one of the handles is that the top quark 100% of the time goes to a bottom quark. Then there's a W boson, which later can lead to two more jets or a lepton and a neutrino. And if I'm looking at the Higgs boson, one of the things which is most difficult for us is to identify the Higgs boson when it decays to a bottom quark and anti-bottom quark. So that B tagging on the right on your picture is used in about 30% of the 700 publications we've had so far. And it's the the technical paper about it has been the 7th most cited journal publication. That's the old method. Okay, so now this is about the concept of heavy particle identification. So let's say that a B quark is produced. It flies a certain distance. You see the dashed line from the primary vertex. It says PB, the primary vertex. And then there's a secondary vertex where it decays. The lifetime in its rest frame is only 1.5 picoseconds. But because of the Lorentz boost, remember there's time dilation, so it flies a bit further. And for high energy B quarks, you get displacements from a few millimeters up to a centimeter, so you can use that. If you consider the secondary tracks, which are associated with the secondary vertex, and reconstruct the invariant mass of these things, you'll get a larger mass because it came from a heavier quark. And you also sometimes will see instead a lepton. If you see that, you also get a neutrino, so it's not really a mass reconstruction problem, but you get another handle on identification. So you use these things to construct the variables to discriminate between bottom quarks, charm quarks, and the lighter quarks. And this is useful for various searches for new physics, for example. So they tried various methods. After years, the best method before was the CSV. SV is for secondary vertex. And there was a neural network with a single hidden layer. There are 20 inputs. about the track and secondary vertex, and about 20 to 40 nodes in the single hidden layer. And the output was essentially B quark versus light quark, so it's a kind of binary classifier. Now in the new case, there's this thing called the deep CSV, and there you see a deep neural network with 100 nodes in each of 2 hidden layers, and now it's more than a binary classifier, so it puts out the probability of being a B and an anti-B, or just a B, or a C and anti-C, or a single C, or light quarks. Whoops, I hit the wrong button. I was. Okay, so this was applied. So you're looking for a rare production of 4 top quarks. And I mean, this could be a sign of something beyond the standard model. Basically, the standard model doesn't give you much, but if there's something beyond the standard model, there are heavier partners in some of these theories to the top quarks, you can get a higher production rate. So the question here is, what is the limit on the production rate in terms of the mass of the extra particle that could be giving you this? Namely, imagine there's a heavy resonance called X, and it decays to 2 Higgs bosons, and then from there it goes to 4 B quarks. So what is the limitation on the so-called cross-section, which is a measure of the production rate, versus the mass of X? And if you look carefully, you'll see the following. So the classical method, okay, is a green, which looks not too bad. But if you start to look at the new deep neural networks, there are 3 of them with different criteria. There's loose, medium, and tight. What does it mean? Loose means you accept 10% background. Medium means you accept only 1% background. Tight means only 0.1% background. If you make it too tight, you start to run out of statistics. So indeed, you find that the best limit, which is the lower one, is the blue, which is the deep neural network secondary vertex finder with the medium tightness criterion. And it's the blue curve. And you compare that to the green curve, and you see it's already the best one, which is impressive because we haven't been doing that for this long. The other is the performance in terms of the efficiency and misidentification probability for such secondary vertices. And you have to then say, what are you talking about? Are you talking about distinguishing a bottom quark from a light quark, which is the solid curves? Or are you talking about now distinguishing a bottom quark from the somewhat heavy but lighter charm quarks, with the dash curves? And so I see one of my little circles is still left over. So I put these little circles there to show where you are with the new method, which is the purple solid curves on the right. It doesn't do that much better with a misidentification probability of 1%, but if then you look for very pure samples and go down here, then you find that it is the best method. And then in distinguishing bottom quarks from top quarks, it's the dash curve. And if I want to do that with 1% background contamination, it's definitely the best. So the next thing is to go on. Remember, the Higgs goes to a bottom quark and anti-bottom quark most often. And we've done a search for that, and we could normalize to see how well we're doing, because this is a known process where the Z, which has a mass of 91 GeV, the Higgs 125, we could look for this. And in fact, we see that, so we know we're doing okay. And then try to find this. Now, there have been measurements of that, but this is a very particular case where the Higgs has a large momentum transverse to the beamline. And so it's telling you something about the dynamics of the Higgs as well. Okay, so now you have this double B tagger. And so this is not yet using a deep neural network. It's about to. And I actually have some of the first results coming. But you can see again, the new curves are the blue curves. And you can see on this the so-called plots, the rock plots with signal efficiency versus misidentification probability. In this case, you look carefully, you see it's reversed. The misidentification probability is on the vertical axis and the tagging efficiency is on the horizontal axis. So the best curves move down and to the right. And you can see that the new technique is doing the best. It's already being used, but then the point is now to improve it further with a deep neural network technique, having seen the experience with a single B quark production. And in fact, it was applied already in a first exercise where you look for the Higgs to BB bar using these techniques, and you see some indication. It's not yet significant, 1.5 sigma, but Z to BB bar was seen as an observation with 5 sigma, which is good. And it's very important to improve this further. So that's work going on right now. Okay, so we have some takeaway messages, which are big messages. You could see we're just starting to get into this field. Machine learning for us has a lot of promise because we have computational problems, a lot of complexity in our methods, enormous computational time. And so perhaps learning from things like scene labeling or from another perspective, the deep neural networks can also provide us advantages in ways that we never suspected before. We want to apply it both for real-time event filtering and a so-called trigger, and also for analysis, and also perhaps reduce the time for simulation. What I didn't have time to talk about today is this worldwide system for workflow, for computation and data storage, and data flowing over networks. And we are building intelligent systems to try to deal with the complexity of those. But once we set those up, then also that would be a very fertile field for machine learning. And that one will have a sort of global impact immediately, because what we do challenges the world's networks. And if we improve those systems, we can improve them not only for a science field, but for everyone. And in the end, the bottom line here is that we hope that by using these methods in many areas, we're going to gain greater insight than we had before. Greater insight in how to solve our problems, greater insight in terms of new scientific discoveries.
I have one question. Your deep neural nets in the examples are not very deep.
Right.
So we're used to hearing about, dozens or even hundreds of layers.
Yes.
Why is that the case?
Well, so you see those are early exercises, and if you look carefully at the computational setup, they're rather simple.
Yeah.
So, I think it's basically a computation problem. We are getting scaling among many GPUs, but haven't really dealt with the issue of the relative connectivity between GPUs and inside GPUs. So if I make a very complex neural network, I'm going to have a problem in a single GPU. Memory limited.
Yes.
For the last bit, how do you know what the ground truth is so you can find the misidentification probability?
How do I know?
If you're saying misidentification probability is like 1%, in order to estimate that, you need to know what the ground truth is.
Yeah, we use simulation to do that. And essentially, so there are always two sides of the coin. One is to use, to make better measurements of processes you understand, and then to apply it, with a slight extrapolation into an unknown area. So for example, we'd like to get better measurements of Higgs to BB bar. We measure Z to BB bar, a known process. We get the right rate, we make an observation, we said we're doing okay. And now this is how we would just translate it to the slightly different case, different mass of a Higgs going to be V bar.
Okay, then I guess follow up. It seems like the most interesting thing for you to find would be something that you're not expecting.
Yes.
And so.
So this is a few general statements about that. So for us, in this language, it translates into what's called anomaly detection. So can you just look at the data and say that something is wrong? There is a trap. Maybe it's like a bear trap. It's like there was a very bright young faculty member at MIT whom I knew well, and he built tools like that, not using machine learning, but using some other methods. The point is that if I have an enormous data set and I just want to look for anomalies, remember there are things I cannot calculate. So there are rare processes, and some of them are either beyond being calculated accurately, and others are just beyond calculation. So we use Feynman diagrams, right? And Feynman diagrams, the philosophy is you have the initial state, the final state. You have to draw all diagrams which start from this, and so it explodes. There are new methods to do certain things. There's things called scattering amplitudes. There's certain things you can calculate way faster than that. But you cannot sort of do a complete calculation. So within our data, there are certain things we cannot calculate accurately. So for example, if I look at all distributions and I say, is there something that doesn't agree with the prediction? So sure there is. What we tend to do is look at our data, and when we're looking for a particular signal, go into a control region, use the data, and then do an extrapolation or interpolation. Because we know there's always something buried in there. So how to say, I've experienced something like that, so I'll talk in those terms. If there was something that really stood out, not just a deviation in certain distributions, but really an anomaly, so we would go through a few things. First, a very deep investigation that there were no detector effects or anomalies in how we took the data. Then you start to go after, so according to my calculations, this could not have happened in the standard model. I don't have a model for it. And then you go after, you know, how limited was my calculation? The final thing, which is what we do live through, is this, and I skipped over some slides that hinted on that, is when you look at with a finite data set, you sometimes see fluctuations, so things are starting to come out. So you watch. And as you take more data, is it getting stronger or weaker? At the end of the previous experimental cycle, the Large Electron-Positron Collider, which was an earlier accelerator in the same tunnel, there was a hint of the Higgs boson at a mass that was at the extreme upper end of what that machine could do. It was 115 GeV or so. Turned out not to be there, but there was a hint. And there was also a question about having multiple experiments. So one experiment had some hint, another wasn't sure. There was maybe some slight hint. So the response was, so run longer. We ran longer, and the so-called signal got weaker. And then we stopped. And then after that, 11 years later, I had a discovery. It was clearly shown that it was not there. It was 125, not 115. There's nothing at 115. So we go through all those things. I'm sorry it's not just a simple answer, but it's a very serious question.
Any additional questions? Well, you've given us a wonderful overview. Thanks so much.
You're welcome. Pleasure. A lot of the work in the last part is not something which I know very much. I learned a lot.